Okay, so at this point we have found out how to compute a derivative at a point, but now we're going to figure out how to find what's called the derivative, and this is called the derivative as a function. So the derivative as a function. So before, when we were finding something like f prime of 2 or f prime of 1 of the same function, that would involve two different limits. So the idea behind the derivative as a function is that we're going to find an equation for the derivative. So the goal here is to find an equation for the derivative. Remember, the derivative tells you the slope of the tangent line or the instantaneous rate of change at that point, however you want to think about it. So what we're going to do is, instead of using an a, we're going to use an x. So recall that f prime of a was the limit as h approached 0 of f of a plus h minus f of a over h. So this was the derivative at a particular point. We want to find the derivative for any value of x, so the limit definition of a derivative is f prime of x, so now this is an equation, is the limit as h approaches 0, f of x plus h minus f of x all over h. So this is a pretty important definition. This is the limit definition of a derivative. So whenever we see something that says find the derivative using the limit definition, this is the equation that we're going to use. A couple of words that we need to know. If f prime exists, then we say it's differentiable. So if f prime of x exists on some interval, then f prime of x is, or sorry, not f prime, f of x is differentiable on that interval. So to find the derivative, it's pretty much equivalent to saying that f prime exists and therefore f is differentiable. Another word that we want to be familiar with is the process. So the process of finding f prime of x is called differentiation. So we differentiate to get f prime. So these are kind of the words you want to be familiar with. The derivative is the equation, f prime of x. If this exists, then f of x is differentiable. The process of finding f prime is differentiation. Another thing that we want to be comfortable with is notation. So there were two people who were developing calculus at the same time. There was Newton and Lagrange. So there's also Leibniz. So we have Leibniz notation, and we also have the Lagrange notation. We've been using Lagrange. So what we want to do is Leibniz. So we have f prime of x. We know what that is. Another way to write this, though, is df dx. That's the same thing. These are just two different notations because two people were developing calculus at the same time. Another thing that we want to be comfortable with is that f prime of, let's say, 2, so f prime of a number, that's the same thing as df dx. And then we draw a line and say x equals 2. Now, depending on the situation, one notation is better than the other. This df dx means take the derivative of f with respect to x. That's what it means. So this says that x is the variable, take the derivative of it. Over here, same thing. Take the derivative of x derivative of f with respect to x, and then plug in 2. So this kind of gives you instructions, whereas they mean the same thing. So these are the two different notations that we're going to use. You want to be comfortable with both because they'll both appear, especially when we get to like multiple differentiation and implicit differentiation. We're going to see one more than the other. So we want to be comfortable with both notations, but again, that's because two people were developing the same idea. One used one notation, one used the other, but they mean the same thing. Alright, so let's do some examples of how we're going to actually implement this. Example 1. Let's find the derivative of the function f of x, where f of x is 2x plus 3. So we're finding the derivative. We're not finding the derivative at a point. We're finding the general derivative. So we're going to use our formula, f prime of x. This is the limit as h approaches 0, f of x plus h minus f of x all over h. So I'm going to use brackets because I think that'll keep everything nice and separated. This is the limit as x approaches 0. Now what is f of x plus h? This says wherever I saw an x in my original function, put in an x plus h. So that's 2 times x plus h plus 3. Then I'm going to subtract off f of x. F of x was just my original function. Then divide the whole thing by h. So what's going to mess you up whenever you go to do this is you want to, first of all, be careful plugging in x plus h. This says everywhere there was an x in the original function, put in an x plus h. Then you're going to be careful with brackets because we're subtracting all of f of x, not just the first piece. Now let's see what we can cancel. We can't just plug in h equals 0 in this equation because we're dividing by h, so we got to do something. So if I distribute this 2, I'll get 2x plus 2h plus 3. Then I'll distribute this negative minus 2x minus 3 over h. Now let's see what cancels. The 3's are going to go away, and the 2x's. So I get the limit as h approaches 0 of 2h over h. H's will cancel, so I get the limit as h approaches 0 of 2. Now what is the limit of a constant function? It's always that constant, so this is just 2. So what this tells us is that f prime of x equals 2. So I found the equation of the derivative. So using this, I could figure out, let's say, what is f prime of 5? Well, the function says regardless of what I plug in, it's going to be 2. F prime of 3, also 2. F prime of 0, also 2. That's what this tells us, is that instead of having to calculate a limit for each one of these, like we were doing before, I have an equation where I can just plug in. So we found out that the derivative was just 2, so the slope of the tangent line everywhere is going to be 2. Now does that actually make sense for this example? Think about the graph of 2x plus 3. 2x plus 3 is a line, goes through the point 3, has slope of 2. Any point I choose, what is the tangent line? So let's say I choose this point here. What is the tangent line? Well, if you think about it, the tangent line actually is just that line, and what was the slope of the line? It was 2. So it kind of makes sense that the derivative is going to be constant because any point I choose, the tangent line is the actual line. So derivative is equal to 2. Let's try a different one. Let's prove that f of x, which is 2x squared minus x, is differentiable. So how do you prove something is differentiable? If you go back to those definitions that we talked about, being differentiable means that the derivative exists. So we're going to find the derivative that'll prove that it's differentiable. So let's find the derivative. So f prime of x is the limit as h approaches 0, f of x plus h minus f of x all over h. Again, until we learn different rules, this is the definition of derivative that we're going to use. This is the limit as x approaches 0. Now I'm going to use brackets again. F of x plus h says wherever I saw an x in my original function, I'm going to put an x plus h. So that's 2 x plus h squared minus x plus h. I'm going to use brackets to keep everything separate. Now I'm going to subtract off f of x. So f of x is just 2x squared minus x. Then I'm going to divide the whole thing by h. So here's the limit that we're trying to evaluate. The issue is we can't just plug in h because we'd be dividing by 0. So let's go ahead and simplify the numerator. X plus h squared is x squared plus 2xh plus h squared. Then I have a minus x minus h minus 2x squared plus x once I distribute that negative. And now let's distribute the 2. So I'll get 2x squared plus 4xh plus 2h squared minus x minus h minus 2x squared plus x, all divided by h. Let's see what cancels in the numerator. Well, these two x squareds are going to go away. What else do I have? I have a minus x and a plus x, and I believe that's all we're going to have that'll cancel. So I am left with the limit as h approaches 0 of 4xh plus 2h squared minus h over h. Now what can I do with this? I can factor out an h from everything in the numerator. So what happens when I factor out an h from everything in the numerator? I'll get the limit as h approaches 0, h times 4x plus 2h minus 1 all over h. My h's will cancel. So I get the limit as h approaches 0 of 4x plus 2h minus 1. Now can I just plug in 0 for h? Well, yes. If I plug in 0 for h, I'll get 4x minus 1. What that tells me is that f prime of x is 4x minus 1. And therefore f of x is differentiable. I just found the derivative. Using this, so these are kind of some examples to do, what is f prime of 2? F prime of 2 would be 4 times 2 minus 1, so 7. What is f prime of 0? That would be 4 times 0 minus 1, so negative 1. So by finding the derivative, you only had to do one limit instead of having to do multiple limits for each one of these. So that's how you would find the derivative. Let's do one more. Let's compute f prime of 2 and df dx, x equals negative 1, of the function f of x, which is 3 over x squared. So I'm trying to evaluate the derivative at two different values. Remember, this is just two different notations, but they mean the same thing. So I'm going to find the derivative, then I'm going to plug in 2, and I'm going to plug in negative 1. So let's start this on a different page. So the derivative of x, derivative of f with respect to x, is going to be the limit as h approaches 0, f of x plus h minus f of x over h. Okay, so let's figure out what is f of x plus h. That's going to be 3 divided by x plus h squared minus f of x is 3 over x squared. Now how am I going to figure out the numerator? I'm going to have to find a common denominator and then subtract the 2. Also, dividing something by h is the same as multiplying by 1 over h, so I'm just going to go ahead and bring that out. So what's a common denominator going to be? I believe it's going to be x cubed times x plus h squared. So I'll get 3x squared over x plus h squared, x squared, minus 3 times x plus h squared over x plus h squared, x squared. So what did I do between these two steps? I multiplied the two denominators and got a common denominator. Then I changed each fraction to have that denominator. So this is the limit as h approaches 0. There, I still have my 1 over h. And let's see what simplifies. So my denominator was x plus h times x squared. Should be a squared here. And then I have 3x squared minus x plus h squared is x squared plus 2xh plus h squared. When I distribute this minus 3, I'll have minus 3x squared minus 6xh minus 3h squared. Now what cancels here? Two 3x squareds go away. So I have the limit, the h approaches 0 of 1 over h. Still have my x plus h squared x squared in the denominator. And now what I'm left with is 6xh minus 3h squared. Let me factor out an h of both of those terms, and you should always be able to factor out an h. So I factored out my h, and now you can see these two will cancel. So I'm left with negative 6x minus 3h over x plus h squared x squared. So I started with my definition of a derivative, simplified it as much as I can, and now I'm down to here. Can I plug in h at this point? Yes, because I won't be dividing by 0, so it'll be negative 6x minus 3 times 0 over x plus 0 squared x squared. Well, 3 times 0 is just 0, so I get negative 6x over x squared times x squared, which is x to the 4th. And now my x's will cancel, so I get negative 6 over x cubed. So that tells me that f prime of x is negative 6 x cubed. Or if we're going to write it in the other notation, df dx is negative 6 over x cubed. Now to answer the questions that we had, what was f prime of 2? Well, I just plug in 2 to my equation. So negative 6 over 2 cubed, negative 6 over 8, which is negative 3/4. I also wanted to figure out df dx, where x is equal to negative 1. df dx, x is equal to negative 1. I'm just going to plug that in. So negative 6 over negative 1 cubed. Well, this is negative 6 over negative 1, so just positive 6. Let's continue this example further. Let's find the equation of the tangent line at x equals negative 1. So remember, what does the equation of a tangent line always look like? Your answer is going to be y equals mx plus b. First thing you're going to find is m. Remember, m is the slope of the tangent line, so m is going to be f prime of negative 1, which we already found. That was 6. Second thing is I need to find b. To find b, you need to find a point on the curve. So we know x is negative 1. The question is, what is the y value that we're going to use? Should I plug it into f or f prime? You always plug it into f. So it's always going to be negative 1, f of negative 1. So what was f of negative 1? Well, my original function was 3 over x squared. So 3 over x squared gives me 3 when I plug in negative 1. Okay, so my equation so far is y equals 6x plus b. I'm going to plug in 3 for y, negative 1 for x. Add 6 to both sides, so 9 is equal to b. That tells me that y is 6x plus 9. So there's my equation of the tangent line. So again, to find the equation of the tangent line, find m. F prime is going to give you m. Then use a point. Always use f here. Don't use f prime to find the point. You always want to use the function, the original function. So that's how you find the generic derivative, and you can plug in points to find the derivative at different points.